Assalamualaikum warahmatullahi wabarakatuh. Dan selamat sejahtera kepada semua pelajar yang tengah online ni sekarang. Harap tunggu sebentar, saya tengah cuba accept yang belum dapat lagi masuk dalam team ni. Sekejap . Halo. Ya, ada lecture lah. Assalamualaikum warahmatullahi wabarakatuh. Maaf ada hal pula. Okey, jadi saya akan sambung. Saya dah buat recording, tapi belum upload lagi untuk kuliah saya yang perlu saya cover. Topik-topik yang saya perlu lecturekan lah. Saya dah buat dah, tapi lepas lecture ni saya akan upload dalam YouTube. So on the secant method, let me see. Tak nampak lagi kan kat skrin kan. Okay. For the topic on postposition method, secant method and modified secant method, macam saya dah WhatsApp tu, saya akan masukkan dalam video. Dah akan upload petang ni. Selalu dah siap dah. So that is the complete which is start with simple fixed point iteration and then Newton-Raphson. Newton-Raphson and then force position, which I'm going to upload it in the video, and the force position and secant method and modified secant method will be on video. Okay. So I'm going to move on to the next topic, which is open the file. Sekejap ni file tu tengah loading. Hello? Ya. Ya. Okay. Jadi termasuk dalam including in chapter 6 is called the brands method, which is not part of the scope. Okay, you can see the title there, called the brands method, but it is not part of the topic for this course. Okay, so you can ignore the topic on brands method, and then let me see. Okay, nampak kat screen open method sekarang. Dia macam dia banyak sangat buka serentak. Okay, brands method which is not part of the scope 6.4 ni. Okay, so you can ignore this topic, brands method. Then okay, multiple routes. Multiple routes means you have more than one route. Okay, so for multiple routes, we apply the Newton-Raphson as well, but the modified. So the modified equation for Newton-Raphson is given as follows. Multiple root. So multiple root correspond to a point where function is tangent to the x-axis. For example, a double root results from fx equal x minus 3, x minus 1, x minus 1 will have x is equivalent to 3 and x is 1 twice. Right? Let's call double root. Okay. A triple root correspond to the case where one x value makes 3 term in equation equals to 0. For example, fx equal x minus 3 times x minus 1 times x minus 1 times x minus 1. Okay. So the root is x equivalent to 3 and x equivalent to 1 3 times. Okay. So that's called triple root. Okay. Multiple root pose some difficulty for many numerical method. This as described in part 2. The fact that the function does not change in sign. Okay. Can so this is the equation for Newton-Raphson equation. for multiple root. Okay. So the difference from the previous Newton-Raphson is the function of f double prime. Okay. So in previous Newton-Raphson, we don't have any f double prime in the equation, only f prime, but now we have f double prime. Use use both standard and modified Newton-Raphson method to evaluate the multiple root of equation 611 with the initial guess of x0 equal 0. So we are going to apply equation 611. Okay, the function is x cubed minus 5x squared plus 7x minus 3. That was the function. It's given here. Yeah, fx is under the topic of multiple roots. Okay, this one after factoring is done. After doing the factorization, this is the equation. But if we expand it, we got this fx equal x cubed minus 5x squared plus 7x minus 3. Yeah? So first derivative yields 3x squared minus 7x plus 7. Okay. So if we substitute inside this equation, then the standard Newton-Raphson equation previously mentioned in my lecture, which is, if you could still remember, the standard equation is xi plus 1 equivalent to xi minus fxi divided by f prime xi. Okay, so xi plus 1 equal xi minus fx. So this is the function fx before taking the derivative. This one is f prime x after taking the derivative. Okay, and once we solve this particular iteration, start from x equals 0, initially x0 equals 0. So this is the answer. We got 0.9976551 after 6 iteration. For the modified method, we have to take second derivative for the function. So the second derivative is f double prime equivalent to 6x minus 10. Then we use the equation for multiple root Newton-Raphson as shown previous in the upper transparency just now, which is x I plus 1 equal xi minus fx multiplied by f prime x. So this is your fx multiplied by f prime x divided by f prime x square. So f prime x square minus fx multiplied by f double prime x. Okay. So we start the iteration from x equivalents to 0, and we see the Newton-Raphson method for multiple root converges very rapidly. Okay, whereby at the third iteration we already got the root to be 1.5 times 0, 2. And the true error is 0.5. 3324, 33324. Okay. So the reason for it to converge during at the third iteration, because the modified formula converge 4 times quadratically, 4 times as fast as the, what do you call it, standard Newton-Raphson equation compared to the, so the modified Newton-Raphson converge 4 times faster than the standard Newton-Raphson method. Okay. So we can also use both methods to determine the single root at x equivalents to 3, because I told you just now, after factorization of the function we got here, so other than x equal 1 to be the root, x equivalents to 3 is also the root. So to get the root for x equivalents to 3, we apply the modified and the standard Newton-Raphson, but using the initial guess of x not equal 4. Just now we use x not equivalents to 0. Okay, and we got the answer approach to 1. To get the answer of 3, so we use initial value to be 4. So you notice the cycle, both of method can be considered to converge quickly, with the standard method turn out to be more efficient. Okay, because until 5th iteration of the standard method, we got the answer of 3.0060 there, with an error through error of 0.00607. Okay, 6 times 0, 2. Okay, whereas here we got 50 in front, or 77 followed by 77. So standard method for this particular second root of x equivalents to 3, which is a single root, okay, turn out to be at the same level as the modified method. So the modified is efficient for repeated type of root. Because x equal 1 is repeated twice, so it's efficient for multiple roots Newton-Raphson approach. See, the x equivalents to 1 twice, so that's double root. We tend to converge faster using multiple root Newton-Raphson approach. Okay. Now look at the system of nonlinear equation now. Okay. All right, system of nonlinear equation. First method that, okay, for example, this one, x squared plus xy equals to 10, and y plus 3xy squared equals 57. So we have two equations and two unknown. There are two simultaneous unknowns x and y, and can be expressed in the form of equation 617. Here, this is the form 617, as xu equal x squared plus xy minus 10 equals 0. That means we bring this 10 to the left hand side. The v equal y plus 3xy squared minus 57. We bring the 57 to the left hand side. Set it equivalence to 0. Okay. So that is u and v. Okay. So the first method that we are going to use is called fixed point iteration. Okay. The fixed point iteration approach can be modified to solve two simultaneous nonlinear equations. This approach is illustrated in the following example. Use fixed point iteration become 10 minus xy, and then the square root at the square we just put it as plus minus. So x is equivalent to plus minus square root of 10 minus xy. Also can, no problem. Okay. And then the b equation, we write it as y equal now. So for this particular example, that's y equal 57, positive 57 minus 3xy squared. That means we keep y on the left. Equation 611(1) can be used to find the new value of x. So this is the initial x and y value to start with. Okay, so we just choose a value that is just so happen here they choose with decimal places, but it doesn't have to. You can start with x equal 1.0, y equals 3.0. Don't have to have a decimal 0.5 there. Okay, so if we maintain with this initial value of x 1.5 and y equals 3.5, then we can write x is equivalent to 10 minus, use this equation. Okay, so 10 minus 1.5 square divided by 3.5. So we have 2.21429. And the result and the initial value of y equal 3.5. So we substitute here now. So you got 57 minus 3. And the x value, you use the latest one we got from the calculation. Okay. Don't use the old number. Otherwise, the convergence will be slow. So we